Now that we've explored circuits experimentally, let's look at some circuit analysis. In this circuit, R1 and R2 are in series, and they are connected to the battery here. If you recall from the lab, we saw that the current that leaves the battery here, I, is equal to the current that flows into R1, out of R1, and into R2. So the current in series is the same for all of the elements. So the current in resistor 1 is equal to the current in resistor 2. And then the current returns back to the battery, and that would also be the current through the battery would be I. So the current through the battery, resistor 1 and resistor 2 are all the same. Now we saw in our lab that when we measure the potential difference, that's the voltage across each one of these resistors. I'll label them V1 and V2. And so we saw that the potential difference across 1 plus the potential difference across 2 would be equal to the potential difference of our battery, which is V in this case. So the voltage adds in series. Let's look at an example. Let's say we have a 12-volt battery connected in series with a 3 ohm resistor that's connected in series with a 6 ohm resistor. Then the wire is going to continue back to the negative side of the battery. So what is the current through each resistor? Now I know, since these resistors are in series, that the current that leaves the battery must be the current that goes into 3 and then goes into 6 ohm and then comes back to the battery. So if I use my rules, I can then use Ohm's law to determine the current in the circuit. So if the 3 and the 6 are in series with each other, the rule is that the 3 ohm resistor and the 6 ohm resistor would add up to be an equivalent of 9 ohms. So it's really like a 12-volt battery is connected to a 9 ohm resistor, and that's all. So our 12-volt battery connected to a 9 ohm resistor. So then I can use Ohm's law to determine the current, because if V is equal to I times R, the potential difference of the whole circuit is equal to 12. That's the voltage of the battery, and that would equal I times R, and the total equivalent resistance of our circuit is 9 ohms. So then our current would be 1.33 amps. So this means that the current through the 3 ohm resistor is 1.33 amps. And the current through the 6 ohm resistor is 1.33 amps also. So I can now determine the potential difference across each resistor. So let's solve for the potential difference across each of those resistors. So now if I use that the voltage or potential difference is equal to IR for each one of my resistors, for the 3 ohm resistor, we would have that the potential difference across, I'm going to use a little subscript here to show that it's across a 3 ohm resistor, would be equal to 1.33, that's I, times R, which was 3. This gives me 4 volts. I can do the same thing for the 6 ohm resistor, which would be that the potential difference across the 6 ohm resistor is equal to 1.33 times 6, which would be 8 volts. Now, if you notice, we will have 4 volts across the 3 ohm resistor. So this is 4 volts across that 3 ohm resistor. And then we have 8 volts across the 6 ohm resistor. And 4 plus 8 equals 12. So now I know that all of my values match up to the rules for resistors in series. A parallel circuit has the components parallel to each other. So let's call this one resistor 1 and this one resistor 2. And then this is my battery, and it has an electric potential of V. So from my lab, I learned that the current that leaves the battery will split, and some current will pass through R1 and some current will pass through R2, and that means that the current through the battery, would equal I1 plus I2. So the current adds up, because as that current leaves that 1 ohm, that resistor 1, and the current leaves resistor 2, so I2 comes on around here, and they get together and make I again. This is a rule for any kind of junction. Like this is a junction here where the wires split. So let's look at then the potential difference across these resistors. Now, because they are parallel to each other, the resistors in parallel with each other have the same electric potential. And if you remember from the lab, we saw that the electric potential of the battery was equal to the electric potential across resistor 1, which is equal to the electric potential across resistor 2. Now let's look at an example where we are using the rules for parallel circuits to solve for the current and potential difference for each resistor. So let's say we have a 6-volt battery connected. In parallel is a 2 ohm resistor, and in parallel with it is a 3 ohm resistor. Now I know that it's parallel because any time I trace the current leaves the positive side of the battery. Remember, that's the long side of the symbol. We look at our conventional current. It leaves the positive side of the battery, and it will get to this point here and this junction, and some current will go down and through the 2 ohm resistor, and some current will go out here and pass through the 3 ohm resistor. So anytime there is a junction, I know that I have a parallel situation. So let's look at what we have here. So the current that leaves this battery, let's say it's I, splits into an I1 through the 2 ohm resistor, and then I2 comes out here, and I2 goes through the 3 ohm resistor. Now what I do know is that these two resistors are parallel to each other. Now a parallel circuit, the components add differently. So remember, our potential was the same for each one of these resistors, but the current is different. So what we have is that I is equal to I1 plus I2. Now if Ohm's law tells us that V is equal to IR, then I could substitute and say that this I right here is equal to, I can be equal to V over R. This would be the potential of the battery divided by the total or equivalent resistance. And then if I is equal to V over R, then this would be the electric potential across that resistor 1 over resistor 1 plus I2, again V over R, and that would be V2 over R2. And if the electric potentials are equal to each other and equal to that of the battery, then all three of these values are the same. So I know that I can divide by V on both sides and they all cancel out, and I'm left with that 1 over R equivalent is equal to 1 over R1 plus 1 over R2. So when we have our parallel circuit, we can determine, and be careful, but we can determine the equivalent resistance of resistors that are in parallel with each other using this equation here. So let's do that now. So to find the equivalent resistance, we're going to say 1 over Req is equal to 1 over 2 plus 1 over 3. So 1/2 plus 1/3 is about 0.8. And that would be equal to 1 over Req, or the equivalent resistance. So in order to find the equivalent resistance, we need to take the reciprocal of both sides. So that gives me R equivalent is equal to 1 over 0.8, which is about 1.2 ohms. So that means that the equivalent resistance of these two resistors together is 1.2 ohms. So now I can think of this circuit as being really like an equivalent circuit, being a 6-volt battery connected to a 1.2 ohm resistor. So this would be the 1.2 ohm resistor, my 6-volt battery, and now I can find the current through the battery because V equals IR, so 6 is equal to I times 1.2. So then the current is 5 amps. Now this is the current through the battery. And now that is the current that is going to split into I1 and I2. So from the rules we saw in our lab, the potential across each one of these resistors would be equal to that of the battery, both of them being 6 volts. So what's the current through each resistor? Well, again, if electric potential is equal to I times R, then we can say that 6 is equal to I times 2. So I would be 3 amps, and 6 is equal to I times 3. So I would be equal to 2 amps. Now I can check to see, I know that the current through resistor, the 2 ohm resistor, which I called I1, and the current through the 3 ohm resistor, which I called I2, should add up to be the current through the battery there. And so 3 plus 2 gives us 5. So that works out.